Hi everyone, how are you doing? Okay, great. Today we will see one small topic which is called polynomial regression. Okay, so yeah, so let's get started in just a second. Okay, so let's start with the topic. Now, just to recall you that we have already seen something called as gradient descent, right? I hope you are comfortable with the gradient descent now. So gradient descent, if I just talk gradient descent in terms of 2D, then it looks like this, which means that there is only one parameter. If let's suppose you have only one parameter, then it will look like this, right? Okay, just a second. Yeah. So which means here can anyone tell me that this W is scalar or a vector? Here this W is, just let me know quickly. If this is the only parameter, then it is scalar, right? I mean, let's suppose there is only one parameter. Then there will be one more dimension for the loss function. Okay. So basically, now in this particular setting, we just have 2D graph. Now, how gradient descent is working? Let's suppose this is your starting point, then it will come down slowly to the minima. We have seen this. Similarly, we have also seen that, I mean, you can apply this gradient descent not just in 2D, you can even apply that in the 3D, which means, or even any dimension, which means that if you want to minimize over these two values, W1 and W2, then this is how it will look in the 3D. And if you want to visualize the same thing that we have seen in the contour form, then this is the 3D visualization and the contour visualization. Okay. So which means that in terms of the contour, you will visualize it like this. In terms of 3D, the same thing will get visualized like this. Is this fine to everyone? Okay. Uh, Now let's just start with today's topic, which is polynomial regression. Okay. Great. This is gradient descent in 2D, this in 3D, this in 3D plus contour visualization. Okay. So let's get started with the polynomial regression. So what's next? Next is polynomial regression, right? Okay. Suppose this kind of data we have, which means that this data doesn't seem to be very well fit in the linear relationship. But suppose this kind of data we have, then tell me, can we use linear regression to model the non-linear relationship? What do you think? Can we use linear regression here? So interestingly, like the answer is yes. Okay. I mean, we can even fit this kind of graph with the linear regression also. Okay. So we will see how. That's called the polynomial regression. Polynomial regression is just, the polynomials which are having, I mean, which are having some degree, which means that the coefficients have some degree, which means that the feature x is transformed into x square, x cube like this. Okay. Anyway, I will just talk about it. So suppose that we want to model some kind of non-linear relationship in a using a linear regression. Then how to do it, right? So what will be the equation of this particular plot? Something polynomial, right? So probably it will look like this, which means that w naught plus w1 x plus w2 x square plus w3 x cube. Maybe till x cube I will stop, or maybe till x power 4 I will stop, or like that, right? So it will be some polynomial. Is everyone comfortable with this kind of formulation? That this is a, I mean, similar formula which you might have seen earlier in your, high school mathematics. But yeah, this is a formula for the polynomial, right? Okay. Now, suppose you want to model the polynomial relationship, which means that your predictions are looking like this. Let's suppose you want to model using this formula. This is anyway y cap. Okay. Then what to do? I mean, I want to do it using linear regression. Then how can I do it? Anyone wants to talk about it? How can I achieve this particular relationship using the linear regression itself? You can speak if you want to. Just let me know. Okay. So what we will doing? Hello, am I audible? Okay. So Shivam is saying that all the parameters are linear. Yes. That's a good answer. So now let's just see that what does this mean. So basically, what we want to achieve this kind of relationship using the linear regression, right? So what we will be doing, we will be treating these features, okay, as a transform features, which means that let's suppose originally you have just x. Now what you did, you have transformed it, which means, or maybe xi, okay, one of the feature xi is there, maybe just x, right? Doesn't matter. I hope that's okay. Even if I remove this I, this is just ith feature. I'm just talking about some random feature, so you can say x only. That doesn't impact, but still, let me just remove this. Okay, suppose your feature is x, right? Now this is your original feature, x is your original feature, but you know that okay, it is possible that it is not able, like we might not able to, model this using the linear relationship, I mean strict linear, in the sense that the feature is x only. So you, what you can do, you can, instead of x, you can use x also, and along with the x you can use x square, x cube, x power 4, like this, right? So you can use these kind of features. Now let's just call this feature as x dash. Okay. So this is x dash or x1 or whatever you like to call it, double dash, triple dash, like this. Okay. So these are the new features. And I don't care about the degree of them. I just see that the one feature is one column. Okay. That's all. I don't really bother in the linear regression. I don't really bother that, okay, that whether it is x square or x cube or what, right? I just say it is a one of the feature. So which means that I will say that x is one feature, x square is another feature, x cube is another feature, x power p is the last feature. Okay. This is what I will say. I mean, this is called feature transformation. And what are your parameters? Parameters are w naught, w1, w2, wp, and so on. Okay. Great. So is this understood to everyone that what I'm trying to say? That this particular relationship is just linear, right? In the sense that okay, you might be a little bit confused that if it is linear, then what is polynomial or like that. See, it is linear in the terms of w nodes, right? I mean w1, w2, like this, which means that you have single or the linear power of this, right? What are your features? They really doesn't matter. Okay, the meaning of these features really doesn't matter. Understood? Yes, we are generating new features, right? So that's what we have been a little bit discussing previously also, that we can even have any kind of features, right? Now you call them, this is a feature one, feature two, feature three, like this. Okay, you call them features. Understood? And then these are your parameters. So do you think there is any difficulty in fitting this kind of linear model using the linear regression? No, right? So you can fit it. Okay. Now, now we will see something. See, uh, suppose this kind of thing is given to you, this kind of data is given to you. Okay. Now let me just take this particular example on the next page. Suppose this kind of data is given to you. This is x, this is y. Can you tell me, if you use y equal to mx plus c, or maybe I mean in machine learning terms, let me write it, w naught plus w1x. Suppose if you use this kind of relationship, do you think it's a good idea? Okay. If you use this kind of relationship to model this particular data, do you think it's a good idea? So it's not a good idea. So what you will do, you will, instead of this, you will say that, okay, let's just do it y equal to y naught plus w1x probably. Or maybe can you just tell me what is good? I mean, x is good, or maybe x square or x cube, x power 4. Which one is good using this particular plot? X square seems to be okay, right? X square, some kind of something this kind of it, right? So so since it is not linear, right? I mean, the better model could be the quartic model, right? So you will say that, okay, let me write like this, which means instead of this you will be using this, right? And now you have just introduced one more feature, which is x square, but the meaning of it or the semantic of it doesn't really matter. You just call it x dash. Okay, great. So so what I just did, I said that, okay, I now will be having two features, x and x square, and now my output is anyway y. Okay. I will be having these as new features. So let me just call it, if you are a little bit confused, let me just call it x dash x double dash. Okay. Or x1, x2, whatever is preferred to you. So let me just call this way. If you are confused that, okay, what is this x square and all, you just call it x2. I hope you understood. Uh, by the way, am I teaching too slow? I mean, probably you might be thinking, right? I'm repeating the things again and again. So you can just let me know if you think that I'm teaching too slow. Okay, great. Now, given this, what you will be doing, you will be applying the linear regression model. Okay. So what you can do, you can think about this in two ways. In the sense that your first thinking is probably like this, that by equal to x square, I mean some ax square, something like this, right? I mean it is a quadratic, right? So what was your first thought after looking at this data? That by and x has this kind of relationship. Okay, probably. How many of you have thought something like this after I asked you that what kind of model may go x square ax square or whatever, x square plus b or something like this, right? I mean this is a quadratic. That is the first thought that might have come to your mind. Okay, but you can also think in this way, that there is a linear relationship between by and x square. See, what I'm saying, that looking at this, you can say in two ways. Okay, what are those two ways? First way is, like, see, the formula is same. Okay, formula is same. Bx plus c doesn't matter. So the first way to look at this formula is that there is a quadratic relation between x and y, right? Quadratic relation between x and y. Okay, which is y equal to ax square plus bx plus c, right? So don't worry, I'm just writing in short, I'm writing x square. Okay, don't think that I literally mean it, which means a value is 1 or b value is 0 okay, I'm just in short, I'm just writing x square. Okay, but it need not to be x square, it could be in this form, right? Great. Now this is quadratic. The second way, can anyone tell me the second way to think about the same thing? The formula will, mathematics will remain same, it is just how you are thinking. Yes, so we can say y is having linear relationship between, can anyone just complete this linear relationship between x square, right? X square, sorry, yeah, x square. So so what I'm saying here, you are saying x and y, there's a quadratic. Whenever you're saying quadratic, you're saying x and y, right? Is this okay? But whenever you're saying linear, you are saying x square and y. Okay, understood. Great. So it is just a way to think. It is not, I mean, not a very great thing. Okay, in the sense that not very much insightful probably. But yeah, it is just good to know. Okay, that you can think in this way, right? Which means they have quadratic relationship. Or probably you, once you introduce, see here how many features you have. Just one feature, for example, just for the visualization purpose. Okay, but probably once you insert, let's suppose x square also. Now how many features you have? This is x, there is one more feature which is x square, right? So now you have two features, and there is obviously y, right? So so you will say that here you have quadratic relationship, but now on the right hand side, what kind of relationship you are expecting on the right hand side? Linear, right? So you can say either this is quadratic or this is linear. Okay, both ways to think are good, I mean that's not an issue. Understood? But mathematically both can be fitted into linear regression. Understood? Okay. So here you can see that we have x and y, and this is model y, some quadratic relationship. So that's good. Now you can even model the same data with a little more higher degree polynomial, right? By the way, how why this is higher degree? Can anyone little bit guess? I mean, by the shape of it, because there are more ups and downs, right? There might be more roots and so on, right? So that's why it is higher degree. Okay, it is just simple curve, so probably lower degree. Okay, or just a straight line, just I mean linear, right? Okay, so it is higher degree polynomial for sure. Now, by the way, which one you think is better, this one or this one? Okay, so I think it was not a good time to ask this question, because everyone has answered second, and I somehow plotted some wrong thing in your mind, in the sense that second is not good. Okay, and why it is not good, you will come to know later. So I think I should have asked that question at that time only, but that's fine. You people are thinking second, but in just few minutes you will get to know that second is not good. Okay, even though it is looking good, right? Anyway, for now, let's not discuss that which one is better, which one is worse. We will come to this, but for now let's just understand linear regression, or maybe polynomial regression. Okay, or technically both are same, but let's just call it polynomial regression, right? Polynomial regression with more slides. So suppose y and x have this kind of relationship. Okay, y is this, x is this. You have multiple choices, as we have seen. You can just have the polynomial of degree 1. Okay, which means here y equal to w naught plus w1x, this kind of relationship, with this polynomial degree 1, which means linear, I mean strictly linear, or whatever you want to call. So basically this is polynomial degree 1 relationship, right? You can model like this. You can model the same data by introducing one more feature, which is x square. And now you can say that y is having the relationship between x and I mean x and y have this kind of relationship. Okay, you can even model with even higher degrees, for example x power 5. Okay, so you can definitely model it using more and more degrees. Nobody is stopping you. Obviously there is a harm, and what is harm we will see it. Okay, even though it is looking good to have better fits, but it's not in that way. Even for example, this is polynomial degree 8, this is too much, right? Okay. Polynomial degree 9 is looking like this, so you can model with other degrees also. So for that you need to introduce that feature. Okay, that's all. Just introduce that feature and use a linear regression. That's all you need to do. Now, for example, this is degree 1, this is degree 2, and degree 50 is looking like this, right? Too much zigzag, too much zigzag. Okay. This is degree 50 fit for some data. By the way, let me just repeat my question again. Which one you think is better? Which degree you are thinking is better? Okay. Degree 1? नहीं. Okay. इतना भी बेकार नहीं. इत- इतना भी बेकार नहीं है degree 2. You remember there was one meme. I just got to remember. In Jab We Met is one of the movie. In that Kareena Kapoor says that okay, इतनी भी बुरी नहीं हूँ, नहीं इतनी भी अच्छी नहीं हूँ शायद. She said something like this. तो degree 2 is like कि इतना भी बुरा नहीं हूँ. ठीक है. So degree 2 is good. Obviously, like degree 1 is very straight, and degree 1 is too simple, right? So okay, in this way, if I just ask you with your logic, will you say degree 0 is best? Do you say degree 0 in the sense y equal to some constant? Is it best? Obviously, no, right? Obviously, no. So, simpler doesn't mean best, right? You have to have some balance. Not too simple, not too complex. But why that balance is needed? That is obviously the question which I haven't answered yet, right? Why that balance is needed? So, this is the balanced one, right? Not too simple, not too complex. Okay, probably you might guess that why too simple is bad, right? Can anyone tell me why too simple is bad? You can speak. It's easy question, right? It's easy question that this is bad, right? You can talk in terms of the mathematics, that if I just say the train error or the train loss, right? Then what do you think, the loss value will be here more, or the errors will be here more or here more? Which one you think? In degree 1 more or degree 2 more? Degree 1, right? So in degree 1, that definitely the loss is more, so definitely it's not good, right? Okay. Now, by degree 2 is good, that probably you might guess that okay, degree 1 is not capturing anything, right? Very straight. By degree 2 is good, And why not degree 50? That is one question that I need to answer, okay, in the future, I mean, as the lecture proceed. Okay. So let's just see more. By the way, we have seen the polynomial regression, which means we are introducing the feature in terms of the polynomial, right? Now, uh, like, if I just ask you that we are having the polynomial features, still, if I just ask you that what is then linear about it, right? What is linear in the linear regression? So let's just answer this question, that what is linear in the linear regression. Okay. So this particular, the algorithm linear regression is basically saying that it has to be linear in bi and linear in W. Okay. If bi is linear in W, which means you can write bi equal to W naught plus W1 into some feature plus W2 into some feature, like this, right? So basically it has to be linear in W. Okay. Now here, do it has to be X only, or can it be X square? Do it have to be X only, or can it be X square? It can be X square also, right? Similarly, it can be X square. So it is just a feature. Okay. The feature is X or X square actually doesn't matter to me. I mean, at least not to linear regression. Okay. It doesn't matter to linear regression. So uh, it is linear. As long as it is linear in W's, it is good. Now, obviously, there is common doubt. Then what is non-linear in W, right? Can anyone give me the example? If I'm saying that, okay, this is linear in W, can anyone give me a good example where you want to say what is non-linear in W? If it is linear, then what do we call non-linear in W? Okay, W square is one of the option. That's true, but is I particularly don't like this example. If you are saying like this, probably let's suppose this is, I'm not much fan of this example. Basically, this is x square, something like this, right? The reason is that okay, there is no benefit of introducing W1 square, in the sense that you can easily say it is W1 dash, it is W2 dash. Okay, you can again say this is linear in W's, right? The parameters are different, that's fine, but it is linear in W's. I don't want to have this as a good example, although technically it's correct, it's not linear in W, but okay, give me some good example. Sinusoidal function, can you elaborate more? Okay. So we will see that what is non-linear in W, but is this clear that this is at least linear in W? Is your machine learning model is trained now to say at least yes on this, that this is linear in W, right? Is this okay to everyone? Okay, at least this is linear in W. That's good. Okay, what is non-linear in W? We will just see. So we are calling this feature transformation as a function of x, which means this could be phi x. Phi x means it could be anything. Okay, this is called phi x. Instead of x, you can even call it phi x. This is just a notation. Okay, don't worry about it. Now let's solve this question, which I've taken from some standard university. So what they are saying, that which of these expressions are linear in theta? Which of these expressions are linear in theta? Is this linear in theta? The first one. Okay. I think you people are saying yes. The second one. Okay, great. The third one. No. The fourth one. Okay, fourth one is tricky. This is just in matrix rotation, right? It is linear in theta. Okay. It is definitely linear in theta, right? I mean, if you can write this, basically it is a linear combination of the columns, right? So it is definitely just theta. So linear in theta. Okay. Similarly, fifth is linear in theta, right? So it's an easy question. So three is no. Everything else is actually yes. Okay. Let's just see this question. Suppose we are performing linear regression using non-linear expansion phi. Okay, which means it could be x square, x cube, something like that. Which of these following statement is true about the learned predictor? It is a linear function of inputs. and linear function of the weights. Okay, there's a question which is basically, I think, aiming to ask you to think in these terms, in the sense that we have seen these two kind of ways, right? Remember these two kind of ways to think about it. So the question is good. Question is actually asking you that whether you have understood this slide or not, right? So let's just see. Most probably that is the question, but let's just read it more. So what they are saying, it is linear function of inputs. So is it linear in x and w? Is this linear in both x and w? So non-linear basis expansion, it means that instead of x, I might be using some non-linear function of it, probably x square, probably sine x, log x, or anything. Okay, so I might be using some non-linear function of it. So since you're even using some non-linear function, can you say it is linear in x? It is linear in w, that's for sure. Can you say it's linear in x? No, right? So that's why A is the wrong option. It is linear function of the inputs and non-linear of the weights. Linear here, non-linear here, known, right? Great. So it's also false. It is non-linear function of inputs and linear function of weights. Yes, that's true, right? Non-linear functions of x and linear function of weights. It is non-linear function of inputs and non-linear function of weights. No, that's false, right? Okay. Although this question I've taken from Standard University, but it's typical looking like a gate question, right? I mean, not too hard, not too easy, just a usual question whether you have understood the definition or not, right? Because see, for you, it might be very trivial question, right? How many of you are thinking that it is a very trivial question? Just let me know. Okay, very trivial, right? But suppose, just imagine that half an hour ago, if someone asked this question, I mean, before this class has got started, if someone asked this question to you, okay, and linear regression, let's suppose, got completed, would you be able to answer in that case? Probably no, right? I'm intending that you might get confused, right? So most probably you might get confused. See, probably you can answer. I'm not saying you won't be able to answer, but probably not that confidently, right? So it is trivial, I agree, but trivial to only those who have understood the definition of linear. Okay, trivial to only those people, which means it is trivial to you because you have understood the definition, which is actually easy definition, but you need to know it. See, you might think that I'm just taking it too much, but actually people doesn't know. In the sense that even if you ask people in the industry, they also might not know. I mean, not I'm not saying that very good researchers and all. I'm just saying beginner level people. I mean, those who are working in ML companies, but they've just started. Just BTech people, those who have just started. Okay, generally they don't know. Wow. So Yashashvi is saying the same same thing, that he was asked this question during one of the interview and it got wrong. Right. Actually, it happens. So that's why I just thought that okay, let's just understand machine learning from very core. Okay, everything. See, whatever it is, even if it is a small definition, I will make sure that it is extremely clear to you guys. Okay. So because I have experience of everything, in the sense that I work in industry, I have been into obviously academics, so I know that what kind of questions they ask in industry, what kind of questions they ask in interviews, and what you need to know about gate D and these things. So I have a good experience in this, so that's why I know that these small definitions are also important. Okay, anyway, now, so correct answer is definitely C. Now, what is non-linear? See, this is non-linear in W. Why? See, it is truly non-linear. Okay. Why that is the case? Because you can't just rename some of the parameters and you can't just say it is, let's suppose, W dash and all, and then it is linear. Can you do it? Tell me. Can you just say that, okay, it is W1? No, right? It is, can you say it is W dash? No, right? Because X is there. X is there. Okay. You can't just say. So it is truly non-linear in W. Okay. Just a simple example where I mean, even this is also non-linear. Technically, this is also non-linear in W. I'm not saying it is a linear or something. This is also non-linear, but I'm just telling you some better examples. Okay. I'm just telling you some better examples. Okay. Let's just see this question. What they're saying, linear regression. What is linear about it? See, you might have noticed that this particular thing is so popular that even at the standard university CMU, right? And that question was also from see this non-linear spreadsheet. The slide of the non-linear is from University of Chicago, and this is this Washington University. So basically, Washington, Chicago, and these things, CMU, and these universities are definitely top notch. So they are talking about it. This is also one very popular university. This is from this university, that what is linear and linear regression. So there are 5 6 top notch universities are talking about that. Okay, just what is linear and linear regression, because people doesn't know, that is why, right? Okay, so tell me, it always fits a linear or affine shape to the data? What do you think? No, right? I mean, it may be like this, right? The shape could be like this. Linear objective function with respect to the input. Tell me, linear objective function with respect to parameters. Okay, some people are saying C. C is false. Can anyone tell me why? Just read this question. Don't get tricked. Read this question, what they're saying. Just have some focus. Linear objective function, right? Okay. Now tell me, is this C correct? Objective function is what? Your loss function, right? Loss function is MSE, which means y minus, and your y cap is basically ax square, or it could be anything, right? A, or whatever. Then basically whole square. Is this linear? This is definitely not linear, neither in W's nor in X, right? So objective function is linear? No. Objective function linear? No. Okay. So B and C are anyway wrong, right? Objective function is not linear in any of the with respect to any parameter. Always puts a linear or affine relationship to the data. Data means that, see, generally what happens that people give you data, okay, in the sense that they have this kind of data, okay. Let's suppose this is the data that they people give you data. Now what you do something called as feature transformation, right? In the sense that now here you have x also, x square also. Can you do it? And then you fit the linear regression. Okay, so this particular phase is called feature transformation. See, people generally give you the data. Now, after the data, they don't care whether you're doing feature transformation, you're not doing feature transformation. They will just ask you, like, okay, whatever model you are giving me, right? So you will say that this is the model you are giving, let's suppose. Then they will say this model is fitting some shape to the data, not the linear, okay, which is not linear basically, some curve to the data, right? So with respect to data, yes, this is a non-linear surface. You're getting my point? What I'm saying? Because generally the user doesn't care whether you're doing feature engineering or then you're applying linear regression, whatever you're doing. They will say, okay, you are giving me this model. You are giving me this model after linear regression, after logistic, after SBM, or whatever you're doing. It is your choice. They don't even care whether you're giving this model after what, I mean, algorithm, right? So this model is something which you are giving to the user. Then user will say, okay, this is some curve I'm fitting, right? So always fits a linear or affine shape to the data. Is this correct? No, right? And B and C are anyway wrong because of the linear objective thing. So what is the answer? D is the answer here. Okay. Okay. See, interestingly, that was MSQ question. Select all, okay, all that apply, and there was nothing correct. See, this is too much, confidence of MSQ. That they are saying, okay, you select all those apply, and there was nothing was correct. Okay, so now let's just see this question. What they are saying, that one of the person whose name was Pijja Pete creates the scatter plot of y against x as shown, right? Which of the following transformation is most appropriate to linearize this data? Okay, they want to have the linear relationship. So they are saying that which of the following transformation is most appropriate? Which one is the correct answer? See, it is not a square root of x, right? It is x cube basically. I mean, some polynomial will fit here. And if you do y cube, it means y cube equal to x or something like this. Then y equal to 1/3. It is not in the square root. So you can see the plots of those. So basically, they will not confuse you much. They are just asking you if you can choose very comfortably. So yes, x cube is the best option here, right? Okay. Now let's just see this. For this, it is just don't worry about the mathematics and all. Just treat this question just a fun questions. Okay. So tell me here, which one you seems to be best? See, right? See here, what is happening? That you are saying there is some sine wave. There is, sorry, there is some sine wave, right? Now this part of sine wave is not much lifted. This part of sine wave is much lifted, then much lifted, then much lifted, then much lifted, which means the amount of lift is also getting increased, right? Which means the amount of lift is basically linear. And on this, I have made the sine wave. So they will actually be lifted in the linear proportion, right? Seems like it is a sine wave plus some linear growth. Is this fine to everyone? So C seems to be the best option, right? Here inside this sine, you also have theta. So basically, it will be like that. Instead of sine x, you have sine 2x or like this, right? Or something like this. Or maybe the theta could be very big number also that you need to train. So it's not like this. It is very simple thing. Okay, as I said, just take it as a fun question, right? Now tell me, is this also linear regression? What do you think? Is this also linear regression? Yes, right? Why? Because you treat this as a feature. This is another feature. Okay. Okay. Now, what they're saying here is that suppose we have a data set and we want to model some particular observation yi using, instead of x, they're using ln of x, right? Or instead of xi, they're using ln of xi. What is minimizer theta 1 cap that minimize this mean square error? Define mean square error. So basically, they want to minimize this, right? So they're asking you what is the best answer. So what you can do, you can just apply the mathematics. Let me go to the solution. So see here that this is your function that you want to minimize with respect to theta. Since it is linear in theta, so most probably differentiation is not difficult. Okay, because it is linear in theta. So if you differentiate this with respect to theta 1, you will be getting like this. You can keep them separate and then you can find out the value of theta 1, which will come like this, right? Tell me, will this be too difficult to differentiate with respect to theta, this particular loss function? Manageable, right? With respect to theta 1, you can do it. And then finally, you will be getting theta 1 as this, okay? It is easy if you do it, okay? Not a very big deal. Now you might remember a little bit, and I'm actually not expecting you to remember. But do you remember we have solved one simple kind of this derivation earlier also, which where I was getting xi by I summation over xy by I upon summation over xi square. Do you remember? Anyone? Okay. Okay. Yes. No, no, there was some theta we have calculated for y equal to, let's suppose, theta naught plus theta 1 x. Okay, if you solve for this particular, using MSE, if you minimize this loss function, if you solve for this, then you will be getting something like this theta 1. Okay, theta 1 star, which means this is the optimal value. In one of the exercise we did, which means that instead of ln x, if I have just xi everywhere, xi everywhere, then it will be xi by I upon xi square. Okay, that's what I'm saying. Nothing much. Okay, so it is a solution one. In the solution two, they are saying that we already know this. Okay, we have solved this earlier. So you can put instead of x, you can put direct ln x. That's what only they are saying. Okay. Anyway, that's fine. So is this okay to everyone? This question, right? Now let's just move to the next question. What they are saying, recall that from lecture that a linear model is defined as model where our prediction y cap is given by the equation below. Okay. So here they are using some transformation. So what is this phi? Can anyone tell me what is this phi? It is basically some function which could be polynomial or anything, right? Okay. So by the way, this has some specific name, and it's not in gate da syllabus. Probably we will not study it. That's called kernel function. Okay, just a name. Has anyone heard about this kernel function, kernelized svm, or these things? Anyone? Okay, kernel you might have heard, right? So yeah. Anyway, so that's not even needed. So anyway, so this is some function, right? This is some function. Now they're saying that which of the following can be modeled using this kind of function? Tell me, is A is the answer? Yes, right? I mean, this is theta 1, theta 2. Inside, I mean, after this theta 1, theta 2, anything doesn't really matter. What about B? B is answer, right? Because theta 1, theta 2, everything else doesn't really matter to me. What about C? Yes, right? What about D? It is a constant, definitely like this. What about D? See, it will be theta 1 x1 square plus theta 2 x, right? With respect to theta 1, theta 2, it is linear. So yes, it is the correct option. What about E? Is this linear? No, right? With respect to theta 1 and etc, it is not linear. So yes, E is not the correct answer, right? Is this understood? Yes, C is just constant. It is just saying y equal to 3. This is my best model I can think of. Okay. E is just like that. We this is not linear in theta 1 in the sense that it is not theta 1 into something, right? So theta 1 is inside some function. You can't write theta 1 into something. So it is theta 1 into something. Okay. So A, B, C, D, right? Great. Now let's just see this. What they're saying. Consider the following training data. Suppose the data comes from this model for the unknown parameter C and B. Use the least square to find the estimates of C and beta. Okay. So they're asking you to find out the estimates of C and beta. So by the way, this is by cap. Okay. So how to do it? One way to do it is this, that you will writing C. So basically Y, three examples are there, right? So Y1, real Y1 cap whole square plus real Y2 cap whole square uh, plus real Y3 cap whole square, right? This is one way to do it. Is this fine? What is Y1? Can anyone tell me quickly? This is 3 minus. What is Y1 cap? C into 1 power beta, right? Similarly, and so on, right? Now, probably I don't know whether it is mathematically convenient or not, but this could be one of the way to find out the loss, and then you need to differentiate this with respect to C, this loss with respect to C, with respect to beta, make them zero, and so on, right? Is this okay to everyone? This could be the one of the way. Or what you can do, you can take the log both side. Okay, if you take the log both side, then you will see that very interestingly, there's a linear relationship between log x and log y. Okay, so if you take the log, it will be like this, and there's a linear relationship between log x and log y. So x was given to you, for example, like this. Okay, 1 1 1, and then it was 0 2 3. So you can have 0, log 2 and log 3. So by also take log, which means it is by in the sense it is after feature transformation, whatever by we were having. So it was data is this, right? 1 2 3 3 1 0.5. right? Now after you take log, it will be log 1, log 2, log 3, which means 0, log 2, log 3. It will be log 3, log 1, which is 0, and 0 log 0.5, right? So you can take log, and then you can say this is my new x, this is my new y, right? This is, you can say, new x, this is your new y. And then you can do your work. And then you can minimize this and then finally find out c and beta. Okay. Great. Now let's just solve more questions. Actually, this is not relevant for gate DA. They will not ask this kind of questions. You just need to know the definitions. Okay. So let's just move to some more interesting part of the lecture. So if I just ask you that which of the following seems to be best or the correct fit intuitively, then what is your answer? We have kept this question on the hold, but this is the most interesting part of this lecture. Okay. Three seems that, okay, this is the best one, right? Three seems to be, sorry, three seems to be the best one. But let me just tell you that why three is not best. Okay, let me just tell you that why two is best and not three. So what you need to do, see here, you need to basically understand one thing, which is called noise in data. Okay. Do you remember little bit I told you earlier? Noise in data, right? Maybe noise is because that doctor is measuring the blood pressure, but his mood was not well, right? It is a noise. Okay, I mean that's why the measurement is wrong. So noise could be because of any reason actually, right? So data is never perfect in our real life, right? So data is always noisy, right? So it means that given this data, suppose, let me just write it here. Suppose this data is given to you. You will say that this data is always having some noise. Okay. And even if it is not having noise or something, still the best is that to basically mostly it will be having noise, but the best is to not remember it too much, but to just have some general trend. See, okay, let's just talk about the noise first. Uh, Suppose this data is having some noise. Then in that case, are you really interested to learn the noise? Are you interested to learn the noise? Which means, let's suppose y equal to fx is the actual function, but there's a noise. There's a real, okay, real y, which actually fx obviously I don't know. I'm saying this is some unknown function, which I try to use linear regression, polynomial regression like that. Okay, this is some unknown function. This is, you can say, some noise. Basically, I mean, data is drawn from some distribution, but there's a noise added in it. Okay, so you really don't want to learn noise, right? See, learn noise in the sense for every point you are taking, doing too much of attention that you are molding yourself based on the points. For every point, you are molding yourself. So, is this a good idea to do it? No, right? Why? Because here we are learning noise. Are you getting my point? We don't want to learn noise. We want to learn general trend. Okay. So what is the problem with learning noise? Because if we learn this noise, then the noise is not consistent in the sense that it doesn't has to have. I mean, if you too much pay attention to the training, then it's not like that. The test will be like following the this noisy pattern. Okay, in the sense that test and train obviously they both are drawn from the same probability distribution, but it may so happen that here basically if you're modeling with the noise, then your model will be having too much be too much sensitive to the training data, right? Because it has not seen the test data yet. So if you learn the noise, it will be problematic to the test data. You don't want to learn the noise, you just want to learn the general pattern. It might not be too simple, like this. It might not be need to be just degree one, just a general trend. Okay, not too much paying attention on the train data. So let me just tell you that this scenario is called overfitting. Okay, this scenario will call overfitting. So what does overfitting means? It means it is a phenomena where the model is unnecessarily complex, in the sense that portion of the model captures the random noise in the observation. This is important. So that's what they are saying, that in the sense that portions, okay, some part of the model captures the random noise, because since it is random, right, there's a problem, right? In the sense that it need not to be exactly with the same pattern or like this in the test data. It doesn't follow any pattern. Okay, so it captures the random noise rather than the relationship. So tell me, do you really want to capture the noise? Do you really want to learn the noise? No, right? You just want to learn the general pattern. That is the challenge in machine learning. You're getting my point? In the sense that you should not be in the case that you are paying too much attention to the training model, that or to the training data, that your model is over learning something. Okay. I will tomorrow I will make it extremely clear. But today I just want to give you brief introduction about the overfitting. As usual, we will do many questions just related to overfitting and underfitting. Okay, just like gradient descent, all the questions I think were theoretical questions, right? Do you remember in the gradient descent? I think all the questions were theoretical questions, right? I mean, whether it will converge, it will not converge. These kind of questions we have dealt with in the gradient descent, just like theoretical questions. Similarly, here also I will have many questions, just a theoretical questions to understand overfitting, underfitting, these things. Okay. Okay. So by the way, you all agree with me that this data always have some noise. Okay. And I don't want to learn noise. Is this okay to everyone? Data always have noise. Little bit you people are convinced. Tell me, little bit at least. Okay. That we don't want to learn noise, and data has noise. That's the problem. Okay. Data has noise, but I don't want to learn it. Understood? So that's the issue. If I learn it, then it is called overfitting, which means for training, I'm being nice, but test, I'm being disastrous. Okay. So see here, uh, just a second. Yeah. See here, tell me, tell me why. Okay. Before I come to that question, first tell me that which area is the overfitting area? A, B, C, D. You have four options. This area is basically the area where you have a models, or a model, your model is having a small training error and a small test error. Here, a small test error but large training error in this area. In this area, large test error and small training error. This is large, both large. Which area you think could be the overfitting area? See, overfitting is doing too much attention on the training data. It means obviously it is learning too closely, right? The training, it is learning too closely. The training, it is having too close learn on the train set. So basically, definitely training loss will be lesser, right? Too much close to the train data. So definitely the training loss will be lesser. Understood? So here, definitely the training loss will be lesser, and test loss or the test error will be more. Why? Because we have learned the noise. Learning noise means I'm not able to generalize. It is the kind of a student. Okay, let's suppose it is a model. Okay, this is a model, right? Model A, which is having this kind of behavior. I mean, this is a higher degree model which is like this. So it is a kind of student who thinks that he is too smart. Okay, in the sense, let's suppose there are many people in the class. He is thinking that he is too smart just because he can answer, or maybe he can understand the things or whatever. Like, I mean, in the class he is doing good, But whenever test is given to him, then he will get to know the reality, right? He's mugging too much, basically, right? He's mugging too much. He's not understanding the things. He's mugging up the training. Mugging up training data doesn't ever help you. Okay. What will help you is to understand the pattern. Don't mug up the training data. Are you getting my point? So if you're mugging up, you can be good in the in the sense that training error will be small, definitely. Right? If you are doing this kind of complex model, then either A or C is the answer. Training error definitely small. What about the test error? Do you think the test error will also be small? Most probably 99.99999% no, right? Because since I have not learned the generalization, my model is noisy, okay, because it has learned the noise. So that's why C is the answer. Okay, understanding the things little bit. Pattern means that just a general trend. Okay, not too complex or not too sensitive. Should not be having that much fluctuations. Just for every data point, I'm running towards every data point कि नहीं, okay, इसको भी सीख लेते हैं, इसको भी याद कर लेते हैं, इसको भी याद कर लेते हैं, इसको भी याद, इतना नहीं, concept समझो. Okay, be go classes, right? Just understand the concept. Don't mug up the formulas. Otherwise, it will be bad on the test. Understood? Okay. So now, little bit you might have understood. I agree that there might be confusions. Okay, don't worry. We will just clear all the confusions. But little bit you might have understood, right? So by the way, let's just answer this question that why overfitting is bad. Can anyone answer this question now? Probably you can attempt to answer. Anyone wants to speak and wants to answer the why overfitting is bad?
Because there is no fixed pattern whereby we should go with.
No, like I mean, okay, but not very convincing. Yes. So because ultimately it will perform bad on the new data, right? Okay. Yes. So it is not generalized. That's a very good way to put it. It is not generalized. Okay. That's a very nice term that I was looking for. See, it is not generalizing. It is just mugging up. You just see, don't think that okay, training error is less than model is good. As a beginner, we might think like this that okay, training error is less, so it is a good model. No, it is a disastrous model actually. If it is learning too much on the training. Okay. By the way, can I? Okay, let me just ask you. I don't know if it is a good time to ask this question or not, but let me still ask you. Can I just say that okay? Let's just have a test data. Can I just say that okay? Let's suppose train error is something, and I want to test whether it is overfit or not. Can I just test it on directly on test data and say okay, this is also less? That's great. It is not overfit. Can I say something like this? Can I test on the test data? See, the training error is something, and I want to just check whether how it is performing on the test data. Training error is low. That I agree. Okay. But I'm confused whether it is having it is overfit or it is good. It is the best thing. It is overfit. Right. I don't know. I don't know in which region, either A or C, because the training error I just got to know it is low. But either A or C, which means it is good or it is has learned too much. So can I just test it on the test data and see whether it is A or C? So ideally, yes, but actually there is just a definition or just a technical catch that I want to just point out that we don't call it test data. We call it validation data. Yes. Test data is something like कि कभी देखा ही नहीं है. Okay. That will come in future and you are in present. Something like this. It means that, I mean, not exactly, but it means that you are not allowed to, check your model capacity, check things about your model, get insights about your model using the test data. Can you get insight about your model using the test data? That okay, this model is overfit or not. You use the test data to get insights about your model? No, right? So we don't use the test data. We just call it validation data. If you want to do it, let's just have some separate data. You call it validation data. That's fine. Okay. Just a technical term I'm saying to you, right? Okay. So I hope a little bit you are able to answer this, that why overfitting is bad. Now let's just go back. Okay. Now let's just have a very important observation. Okay. So this is a very important observation. Actually, not a very important observation. It is a very, very important observation. Okay. So one thing I just like to point out here, which is very important thing, that polynomials that overfit often have large coefficients also. See, large degree is one thing, large coefficients also they have. For example, suppose these are the two polynomials. Okay. Here, let me just tell you, surprisingly, both of these polynomials are having same degree. Okay. Both of these polynomials are having same degree. But but this particular polynomial seems to be too fluctuating, right? Because if there are 2 points, it is taking too much into account. It is just passing through these 2 points and then coming back, then passing through these 2 points and then going like this and like this, right? It is learning too much. So which is a overfit here? Which is a overfit here? Which one you think? Let's suppose it is one, and let's suppose this is two. The second one, this is two. Which is overfit? The second one, right? Second one seems to be overfit. Why? Because it is learning too much. It is learning every training data point. For every training data point, it is changing himself to twisting twisting too badly, right? Here and there, just to learn these two. It is again coming back and going forth and so on. But it is not learning too much, right? It is okay. I mean, nice, good pattern, smooth like this, right? Sorry, something like this. Okay. So both are having same degree. Still, one of them is overfit. Another one is not overfit. What is the reason? The reason is that it is observed. Okay, obviously mathematically also proved by few people, but we will not go into those things. So it is basically observed that if it is overfit, then or in other words, that if it is having, let's suppose, larger coefficients, okay, the larger coefficients, then it is tending to be overfit. Okay. Why is blue line overfit? Because it is twisting, like that line itself too much for every data point. For example, to learn this, it has come from somewhere, and then it wants to learn these 2 points. Okay, I mean passing through these 2 points, then again going forth like this, then passing through these 2 points. Right? Every point it is passing through, going very closely to every point. But this is not twisting. It is smooth, right? It is not smooth. It is not doing too much. It is just a smooth curve. So that's why you can say that intuitively I'm just saying that okay, this is not overfit, this is overfit, because this is having a small, very small training error. How much training error? What do you think? I think almost zero in this case, right? Almost zero. It is going through all the points. Almost zero training error. So if the training error is low, then it is a very good sign for the overfit, right? Okay. So so given that both are having same degree of polynomials, still this is overfit and this is not overfit. This is a very good observation. Okay. So what we ultimately want, what do you think? We want weights to be lesser, right? We want the weights to be lesser, because for the given polynomial having the same degree, if weights are less, then I will prefer the second one, which is having the weights, which is having less weights, because it most probably it is not overfit, right? Is this okay to everyone? This exact slide I have taken from University of Toronto. Okay. So the thing is that polynomials that overfit often have large coefficients. This is the observation. Hence, we want our weights to be smaller. Is this fine? We want our weights to be smaller. Let me know. Right? Okay, great. Okay, this is a joke. that I only made, I only written. I don't know if it is good or bad, but yeah, this is a joke that I thought that it just came to my mind. I don't know why, but yeah, that when your machine learning model hits the gym, so we will ask the model, why did you? Okay, we are just asking, why did our machine learning model start a diet? So why did it start a diet? Because it was overfitting and needed to lose some weight. Okay, so the model started dieting. Anyway, I don't know if it is making sense or not, but yeah, just came to my mind. So thought, okay, let's just put it. So basically, you can say that higher weights are not just bad for the humans; it is bad for machine learning models also. So with this, you can definitely say that AI can replace humans, right? Because they also care about their health. They also don't want to be too much heavy. Their models also don't want to be too much heavy, so they probably they can replace humans. Okay, anyway, now you might remember this, that they also don't want to have overweight, right? Is this fine to everyone? Okay, great. Now let's just move to the next slide. So what they're saying, that there is another reason to keep the weights small, right? What is the another reason? See, one of the reason we have seen that if their coefficients, weight coefficients are, just a second, are larger, then they're tending to overfit. We have seen this. Or in other words, if this is a overfitted model, then the coefficients are large. But there is one more reason. What is that reason? The reason is that suppose the following two weight vectors W and WE make nearly the same predictions. For example, this is also giving the nearly same and this is also giving the nearly same. Can you tell me why WA is better than WB? Other than the previous region, which is weight is less, can you tell me why? I mean, other than that, it will overfit or something. Basically, not linear. It is basically this particular is actually little stable, and this is very sensitive in the sense that if you have, let's suppose, y equal to w naught plus w1x, and here w0 and w1 are this. Okay, this is w0, which means according to one of the relationship it is 1 plus x, according to the second relationship it is minus 9 plus 11x. Okay, now tell me, if x is, let's suppose, 2, then y will be something, right? Let's not calculate it, but y will be something. But let's suppose here x is 2, then y will be, okay, or maybe I can just quickly tell you. See, let's suppose I have two models. What was that? Minus 9 plus 11x. See here, if x is, let's suppose, 1, right? If x is 1, then y will be, or maybe x is 2, then y will be 22 and then minus 9. So it will be uh, uh 13, and then if here x is 2, it will be uh, 3. Okay, but now suppose you change from 2 to, you change 2 point, 3 or 2.5, or little bit variation you take. Now it will get changed, since you are adding half of this, I think 5.5 or something, right? So y will get changed to 13 plus 5.5 or something, right? I'm not sure. Is this correct? I think, right? Okay. Now here you change from this 2 to 2.5. Then let's just see that how y is changing. What will be y? 3.5. Is this correct? So it is dropping from, or it is changing from 3 to 3.5. It is changing from 2. Oh, sorry, it is changing from 13 to 18.5, which means literal change in y is giving you more, little change in x is giving you more impact on y. Is this a good thing? Do you think it's a good thing? Maybe little bit variations will be there in the measuring, or all right. The data may be having little bit change and so on. So little bit change should not be fluctuating too much, right? So that's why also see, again, I have taken this from the University of Toronto only. That's why also we want weights to be smaller, because the smaller weights are stable. In contrast, W is more stable, providing consistent predictions even with the minor input variations. Let me know if you understood this. Are you getting? See, ultimately, we want weights to be smaller because higher weights, even the polynomial degree is same, higher weights means they might tend to overfit. Also, this is very unstable. Higher weights are unstable because little change in x will give you, too much fluctuation in y, which obviously you don't want, right? So higher weights are unstable also. Also, they tend to overfit. They're complex also, right? They're leading to the complex models and they're unstable also. Getting my point? So these are the two reasons we have seen today to not have the higher weights. Okay. The larger coefficients. Why? One thing is because they tend to lead to complex models. Complex models basically learn noise, right? I mean, they're too sensitive to the noise. The second thing is that they're unstable, right? They lead to. Anyway, you don't need to remember the region. Just remember the outcome that we want to have ways to be smaller. Because I don't want a complex model, or maybe this is easier to at least understand that I don't want that much variation. Okay, I don't want too much of variation that okay, little change in x is leading to too much change in y. I don't want it. Understood? So that's why overfitting is overall a bad idea. Because if you are too much learning the noise, you want to be able to generalize. So why it is bad? Because of no generalization. Okay. What is overfitting? Overfitting means you are having a small training error. It is very good on the train, but when it sees the test, it is not able to perform. Okay, cool. So now let's just understand this overfitting and underfitting in bit more detail. Not just bit more detail, in a too good detail, right? We will understand what is overfitting. There is one more term called underfitting. We will understand both of this, okay, very nicely with some help of some examples and all, right, and some questions. So that we will do in the next class. So today we have just understood that what is a polynomial regression and what is the introduction to overfitting, right? Probably you might have got it a little bit. Now we will see it more. Understood that what is overfitting. By the way, anyone wants to answer me quickly why overfitting is bad? Don't remember it. Why overfitting is bad? You need to answer it quickly, just in one word, or one or two, three words. Yes, it is learning noise. This is a very good answer. In other words, it is not able to generalize, right? So both are extremely good answer, equally good answer. So it is learning noise. Okay. I don't want to learn noise. That's why outfitting is very bad. Understood? Oh, great. So let's just meet in the next class now. Yeah. Thank you, everyone. Take care. Bye bye.